Hey guys, Dr. Thomas. We're getting near the end of chapter 4. We're at the section starting titrations. I'm on slide 27 of the PowerPoint. So let's talk about what a titration is. It's a very exact reaction done in chemistry. It's a pretty common technique where essentially I put one reactant and put into a beaker or flask. Often with a titration, probably the most common use of this is when we're reacting an acid and a base. So most of the time, an acid will be put in the flask. It's a specific amount of the acid, meaning if we use a pipette or some other accurate piece of glassware, we can add a volume that is known to the flask. So we know how much acid's in there, okay? Then, when we do an acid-base reaction, most acids and bases are colorless. So when they react, it's a double displacement reaction. It forms a salt and water. Neither of those has any color. So in order to see the reaction occur, we have to add something called an indicator. So right here, they're adding an indicator. The most common one that we use is phenolphthalein, which is a big long name, but it's a compound that in an acidic solution, it has no color. But once you add enough base to make the solution turn a little bit basic, it'll turn pink. So essentially that's what we're going to do is when we're going to have the flask with acid and the indicator, it has no color. Once we start the titration, the base, which is most commonly it's sodium hydroxide, is in a burette. The burette has a valve near the bottom. If you turn the valve, you can make it drip out one drop at a time, and you have very nice control with that valve if you've practiced with it. But you want to keep adding sodium hydroxide from the burette until you get to the point where you add one drop of sodium hydroxide and the solution turns pink. Now, we want it to be the faintest pink color possible to be accurate, meaning the solution was acidic the whole time. As you add the base, the pH of the solution in the flask goes up, 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 up. When it gets to be neutral, that's the point where the acid and base have both neutralized each other. And then when you add one more drop of the base, that's when the phenolphthalein turns pink. That's the point where you know you're done. Often it means that you went a tiny little bit past the end point, but it's usually close enough that you can still get really good data. If you know what you're doing with titrations and have practiced a lot, you can get percent error on your experiments that is well below 1%. I think often it's like 0.2 or 0.3%, which is, for any chemistry experiment, that's a very, very low percent error for you to get, and that's good, okay? So that's the idea, is that we have a base in the burette, acid in the flask, we add until it turns pink, and by doing this, we can solve for an unknown value. Typically, when you do a titration, you're usually looking for the concentration of either the acid or the base. Now, you have to know one of them in order to find the other one. When we do the experiment, there can only be one unknown value we're looking for. So, if I'm looking for the concentration of the acid, that means I need to know the concentration of the base, or vice versa. All right, so our general process, we do the titration. The amount of the acid in the flask is a constant value. You pipetted either 10 milliliters or 25 milliliters or whatever. So you should know exactly how much acid's in the flask. The number that you have to calculate is going to be from the burette. Again, usually it's the base, but you're going to drip in a certain amount from the burette. You have to make the initial reading on the burette before you start. You're going to add drop by drop until it turns pink. Then you stop. If you know the initial volume reading and the final volume reading on the burette, the difference between them tells you how much you've added. Okay? So you have to find the volume that it takes to reach the equivalence point, and that's the point where when you add that one more drop, it turns pink. Okay? So if you can find out what the volume of the base is from the burette, you're going to use that value. You're going to convert the volume into moles. Molarity times volume gives you the moles. Then you have to have the ratio from the balanced equation to go from the moles of the one thing that you know to the moles of the other thing that we're trying to solve for. And then finally, once you know the moles of the unknown, then you can use the moles and you know the volume of that. The moles divided by the volume is going to give you the molarity. So that's our path that we generally are going to be following when we do a titration. So we have a problem. I have 31.5 milliliters. An aliquot is a sample. It's just a fancy word for a sample. So I have 31.5 milliliters of the acid solution in a flask. I'm going to add my base concentration is 0.0134 molar. Now, that's the number I'm going to use as a reference to be able to solve for the unknown acid concentration. So when I'm using a number as a reference, it's called a standard. So this is a standard solution of sodium hydroxide. Someone else has already previously determined this number for me, so I'm going to use it now as a reference value. Okay, and again, every time you do a titration, you have to find the concentration of your reference before you can find the concentration of the unknown. Okay, in this case, it's already done. They gave me that number. So I know the concentration of the base, I know how much of the base was added, and I know the volume of the acid that was added. So based on that, I should be able to set up my calculation. So I'm going to start with the compound that I know everything about, the sodium hydroxide. I know its volume and molarity. So on my mole map, I'm going to go from the volume of A, I'm going to find the molarity of B. Okay, so the volume of the base, 23.9 milliliters. I'm going to convert to liters. That's going to be 0.0239 liters of NaOH. Multiply that by the molarity, which was given is 0.0134. That's the moles per liter. Okay, I'm going to switch to black because the green's not showing up very well. But so that's the volume times the molarity to give me the moles of sodium hydroxide. Then I need the ratio. So if I wrote the reaction, I should do that. Nitric acid plus sodium hydroxide. When you write the reaction and balance it out, it ends up being 1:1. So it's going to be 1 NaOH to 1 HNO3. And then finally, at that point, liters have canceled, sodium hydroxide is canceled. So at this point, I have moles of HNO3. I want the molarity of HNO3. And I know molarity is moles per liter. I have moles up to this point, so all I need to do in my last step is divide by the liters. This is the liters of the acid. I have the moles of the acid. I want to divide by the liters of the acid to get the molarity. So the liters of acid is 0.0315. So if I work that out, 0.0239 times 0.0134 divided by 0.0315. I got that the concentration of the acid was 0.0102. 0.0102 molar. Again, pay attention to your sig figs. All the numbers given had 3 sig figs, so my answer should have 3 sig figs at all. Also, so that should be my answer. Now, there is a shortcut. When you're doing a titration and you have 2 liquids, you can use an equation that's very similar to the dilution equation. MAVA equals MBVB. So if we remember, for any solution, the molarity times the volume gives me the moles. So the moles of the acid on this side are equal to the moles of the base at the endpoint. Meaning in a titration, if I've added exactly enough base to neutralize the acid, then the moles should be equal in a 1-to-1 reaction. So if this equation is true, I should just be able to plug in the numbers from the problem into this equation and solve for my unknown. So if I do that, Number one, I'm solving for the molarity of the acid. So Ma is my unknown, so I'm going to plug in an X. Va, the amount of the acid I had was 31.5 milliliters. Mb, the molarity of the base, is 0.0134 molar. And the volume of the base was 23.9 milliliters. Now remember, when I use M1, V1 to M2, V2, as long as my units on both sides match each other, I can leave it in milliliters. So essentially with this setup, I should be able to solve for X, and hopefully I'm going to get the same answer that I got up here. It's just two different ways of working the same problem. So let's try it. I'm going to multiply these two, divide that one under. So 0.0134 times 23.9 divided by 31.5. And guess what? I did get the same number. X equals 0.0102 molar. So that's a shortcut. Instead of working all the way through a mole map, if you're doing a titration where you've added the exact amount of the acid and base that it takes to neutralize each other, then I can use this titration equation, which is very similar to the dilution equation, to solve the problem. Now, there's one more warning on this problem. If we use a titration problem, we want to use this equation. This equation only works if it's a one-to-one reaction, because we're setting it based on the moles of the acid equaling the moles of the base. Well, the moles will only be equal if it's a one-to-one reaction. If it's not one-to-one, we're going to adjust our equation slightly. I'm just going to divide both sides by the coefficient. So it becomes MaVa over Ca equals MbVb over Cb. This will work for any reaction as long as you have the balanced equation. As long as you know what the ratio is, you're going to plug in the coefficient of the acid under the acid side and the coefficient of the base under the base side. At that point, you could solve the problem just like we did. Okay, so that brings us to the next problem. So the next one, I'll read it. 31.5 milliliter sample of a sulfuric acid solution. So basically it's the same numbers as on the previous slide, but now I've got sulfuric acid instead of sodium hydroxide. So if I'm paying attention, and it's really easy to get mixed up, but you always, when you do one of these, if you don't have a reaction, you should write it out. It's sulfuric acid plus NaOH. When you write the products, it's going to be sodium with sulfate, Na with SO4. But I know that sulfate's -2, sodium's +1, so it has to be Na2SO4. And then I make H with OH makes water. So then when I balance it, I'm going to need 2 there and 2 there. So that's my balanced equation. Notice that this time it's 1 acid to 2 bases. So when I start plugging my numbers in, that 2 there on the base has to go here, the coefficient of the base. Okay, so based on that idea, let's plug our numbers in. So the volume of the acid is 31.5. The molarity of the acid is my unknown. The coefficient of the acid is a 1. Equals. The molarity of the base is the 0.0134. I should be putting units, milliliters and molarity. The volume of the base in this problem is 23.9. And then my coefficient of the base is a 2. So now if I solve that one, shouldn't be half the previous one, 0.0134 times 23.9 divided by 2 divided by 31.5. So this time I got 0.00 0.508. So X equals 0.00508 molar. So that would be the concentration of this unknown sulfuric acid solution. All right, good time to cut it off.